Okay, so we laid a bit of a foundation in 14.5. We looked at the potential energy due to gravity, the potential elastic potential energy. We saw that the work done by conservative forces from 1 to 2 is equal to V1 minus V2. And inside V1 and V2 are both, well, if you have both, it has the potential energy due to gravity, the potential energy in the spring at state 1, and the potential energy in the spring and gravity at state 2. Okay, so this is very useful for us now. Recall that what is the principle of work and energy? It was given by T1, the initial kinetic energy, plus all the work done on the particle from 1 to 2 would give us the kinetic energy at state 2. Now, the question I have to you is, what were all the forces, the different kinds of forces that we've been seeing? Well, we saw a spring force, we saw weight, and we saw friction. We did see others, but I'm just going to focus on these now. Okay? So, in the principle of work and energy, we could potentially have had work done by a spring force, work done by weight, and work done by friction. Now, if we can break up this work over here into T1 plus the work done from 1 to 2 by all the conservative forces, plus the work done from 1 to 2, some of the work done from 1 to 2 by all the non-conservative forces. Okay, so we've just broken up this work done into the work done by conservative forces and non-conservative forces, and we equal that to T2. Okay, it's exactly the same as this. Now, if we identify in our problem that we only have conservative forces acting, and we do not have any friction in our problem, then we can throw this away. And we just have T1 plus all the work, some of the work of the conservative forces equal to T2. Now, we already saw that the work done by conservative forces from 1 to 2 is the change in potential in the potential function. Okay? So, what are we going to do? How about we just replace this with V1 minus V2, right? Because that's work from 1 to 2 by all the conservative forces is V1 minus V2. Okay? And this equals T2. So we can end up with this equation over here, which is called the conservation of mechanical energy. Conservation of mechanical energy. The kinetic energy at state 1 plus the total potential energy at state 1 is equal to the kinetic energy at state 2 plus the potential energy at state 2. This happens only if we've got conservative forces. Only if we've got conservative forces acting on the particle. Okay? So what this means is that we are conserving energy. The total energy at state 1 is equal to the total energy at state 2. I'm not saying that T1 equals T2, and I'm not saying V1 equals V2. No, I'm saying the total energy at state 1, kinetic plus potential, is equal to the total energy, kinetic plus potential at state 2. So let's look at an example. Here we have a ball which starts from rest at the top, from a height, and we drop it towards the floor. First of all, what are the forces acting? The only thing I can see is weight. Yes, there's friction due to wind, but we're not going to look at that. So in our problem, we have only weight. And we know that weight is a conservative force. So, because we only have a conservative force acting on this particle, we can apply the equation, the conservation of mechanical energy. So, without going into too much detail, we know that the total energy at state 1 is T1 plus V1, right? We know that the kinetic energy is 0, and the potential energy was WH. Okay? So the total energy at state 1 is WH. And because it is a system with only conservative forces, we should expect at every point along here, at every state that you look at, for the total energy, which means T plus V, the total energy should remain the same. So let's look at this. So the energy at this top state, state 1, is WH, which is just, it is purely potential energy here. Okay? Now, what is the total energy? The total energy at state 2. Well, at state 2, I'm not going to go into all of this. At state 2, which is T2 plus V2, is equal to this long thing, and we see that it is also WH. The total energy stays the same. And then if it drops all the way down to this point over here, which is T plus V at state 3, we see that it is also WH. So the energy, the total energy, has remained the same at every single point. This is the conservation of mechanical energy. So over here they say at the top here, potential energy is maximum, kinetic energy is 0, right? Then over here we have potential energy and kinetic energy, and over here we have 0 potential energy and maximum kinetic energy. So all the potential energy over here has been converted into kinetic energy down here, but the amount, the total energy, remains the same. Okay. So also we can apply this to a system of particles. Perhaps we'll do an example on that. Okay.